So let's start off with, this is not in your notes, but let's just start off looking at this question here. So I have this question, and it's kind of a weird statement. So we got to figure out what this exactly means. So we're kind of trying to figure out what's with this question and what is it asking. So we know that this is asking you to calculate the derivative. This is asking you to calculate the second derivative, or the derivative of the derivative. So d with this, what looks to be a squared, so d squared y divided by dx squared is the second derivative with respect to y, is what that's saying. So the way we read this is that give us the second derivative with I said that a little bit wrong. The second derivative with respect to x of function y. And so, so let's go ahead and do that on this example here. So we're going to differentiate both of these terms in function y. So we got to look at this term here, and some people might automatically jump to the quotient rule here, but you don't really need it, because with just this 9 in the bottom, we can really think of this as 1/9 times x cubed. So we're going to go ahead and think of it like this, and so this is just a coefficient. So when we do the derivative, when we do the power rule on this term, it's going to be 1/9, and then we're going to do the power rule here, 3x squared. Then we get a minus sign, and then we're going to differentiate x, which is 1. So when we simplify that, we get 1/3 x squared minus 1. Okay, so this symbolism is saying let's take a second derivative of function y with respect to x. So that just means differentiate again, just go through the power rules again. So similarly to the original function, we have a coefficient that's just a fraction. So when we differentiate that, we have 1/3, and then the power rule on this is going to give us 2x to the first power, and then the derivative of this is 0. And then we can just kind of make this look a little nicer. That ends up being 2/3 x. So sometimes I'll ask you for remember these are called higher order derivatives. We can keep differentiating. If we've got continuous polynomial functions, we can just keep differentiating them until we've eliminated all the powers in the function. Or we could write this 2x over 3. Okay, so today's focus for day 4 for section 3.3 is really getting some fluency here with the derivative rules. So let's first recap our two main rules here, the product rule and the quotient rule. So the product rule is the derivative of the first times the second plus the first times derivative of the second. And then the quotient rule is that you have to think that, you know, the little reminder of low d high minus high d low over low squared. So by low we mean the bottom or the denominator. So low would be function v and high would be function u. So low d high would be v derivative of u, so vu prime, minus high d low would be u times v prime. So notice how similar this is to this. It's the same derivative and function pattern, just with a minus sign, and then all over low squared. So just we're going to kind of keep in mind the product and the quotient rule and use them when we need to use them. Okay, so we talked a little bit about it in that first example that wasn't in your notes, but higher order derivatives is just taking the derivative of the derivative and keeping and repeating that process. And so I call higher order derivatives rinse and repeat, because you just keep differentiating your result. So in respect to that, then let's take a look at the notation. So we know dy dx or y prime, that's the first derivative. So the second derivative, then we would call this y double prime. We could say the derivative of y prime with respect to x. And this is kind of letting you know where the notation comes from, but the derivative of y prime with respect to x is really the derivative with respect to x of dy dx. And so that's why this notation is the way it is, because since we're taking the derivative with respect to the variable of a derivative, then we literally on the top, in terms of the notation, have d times d, or d squared y, and dx times dx or dx squared. We don't typically put brackets around that for the notation, otherwise it gets a little messy looking. But that's why the notation is the way it is. And then we could do a y triple prime, which is a third derivative, which means if we'd used this notation up here, it would be d3y dx3. We don't typically do that, though. We usually just use the triple prime notation, and then we can keep going on. Notice the fourth derivative is taking the derivative of the third derivative, and at that time, you could use still 4 little prime marks, but that's getting to be a lot of marks up there. So typically, we put brackets and a 4 up in the power location. The brackets are important because you don't want this to be misinterpreted as y to the 4th power. The brackets tell us that this is a higher order derivative number. So that's why I call this rinse and repeat, because we start with a function, we differentiate it, we take that, stick it down here, differentiate it again, get a result, stick that down here, differentiate it again, get a result, stick it down here, differentiate again. Okay, so like I said, really these 9 examples are just to get you some fluency with the derivative rules, so that you're a little more competent when you differentiate expressions. So what you might want to do is you might want to stop the video, try number 1 on your own, and then run the video to see if you got the right answer. And if not, then you can get clarification at that time. And you probably want to proceed through the other, all the way through question 9 in that fashion. So if you want to stop the video now, I'm going to start explaining question 1. Okay, so here's the explanation for question 1. Question 1 is a polynomial. It's a binomial because it's 2 terms. So we're going to need the power rule here. So we're going to bring the 3 down, multiply it by the 7, make a 21, reduce the power to a 2. Minus sign stays where it is. We're going to bring the 5 down, change that to a 20, reduce the power to 4. So here's the derivative. For number 2, here's the explanation for number 2. So I guess before I go into the explanation, you might want to pause the video now and try 2, and then come back and turn on the video for the explanation. Okay, so here's the explanation for 2. Notice the top, you can factor out, actually you can factor out 3 powers of t, technically, but I just factored out 1 power of t. And then that enables you to cancel t on the top and bottom. So I kind of call this divide and conquer, because when you divide out the t, top and bottom, to simplify the expression, then we're left with just a polynomial expression like example number 1. And so we can just use the power rule here. So we bring down the 2, multiply it by -2, get -4, times t to the 1 power, that's the reducing the power by 1, and then bring down the 3, multiply it by 5, get 15 t squared. So at this time, you might want to pause the video and try number 3 on your own, and in just a second here, I'll explain number 3. So the trick for number 3 here, and this whole chapter or unit is kind of helping you develop, they're not really tricks, but they're strategies and techniques, I should call them, so that you can differentiate expressions. So the strategy here is to recognize that this should be FOILed out so that you can get your polynomial. So 3w squared minus 5 times 3w squared minus 5 is 9w to the 4th, minus 30w squared plus 25. And now I have a trinomial, right? 3 terms. Trinomial, and it's just polynomial in nature. It's just powers, so I can do the power rule. So I'm using my prime notation here, so f prime of w, bring the 4 down, bring the power down, multiply by 9, get a 36. W to the 3rd power, bring the 2 down, multiply it by -30 to get -60. W to the 1 power, or just w, and then the derivative of 25 is 0. So at this point, you're going to want to pause the video, and in just a few seconds, I'll go and give you the explanation to number 4. Okay, so for number 4, we're kind of upping the ante here. We're getting to more complicated expressions. These are no longer polynomial in nature because they're no longer integer powers of x and positive powers of x. But we can still use the power rule. That's the nice thing about the power rule. Is the power rule, you're just subtracting 1 from the power and bringing that little power down, multiplying it by the coefficient. So what we need to do is we need to rewrite all of these so that we don't have these fractions here. Now, really, I mean, because you have a fraction for the middle term and a fraction for the last term, you could do the quotient rule on each one of those, but that gets really messy. So I'm going to rewrite it like this. 4x to the 1/3 is fine. That's just a power of 1/3. Then I have my minus, and I'm going to write this 4x to the minus 2. So that's a way of getting rid of the fraction and writing it as 4 times x to the minus 2 instead of 4 divided by x squared. And then I have a plus, and I'm going to do the same thing here. Now this is the tricky part, because the only thing I move is the root x. The 3 needs to stay in the denominator. So this is 5/3 x to the minus 1/2. Remember, square roots are a power of a half. So this is a minus 1/2 because we moved it because it's a square root and we moved it from the bottom to the top. Okay, so now I have everything written as a power without any fractions. So now I can just do my power rule. So again, my power rule is bring down the power, multiply it by the coefficient, and then subtract 1 from this power. So let's take a look at this first one. I bring the 1/3 down, multiply it times 4, and then I have to subtract 1 from 1/3. So you're going to want to think 1/3 minus 3/3, and that's a negative 2/3. So that's my new power. And then we have a minus, and then I bring the negative 2 down and multiply it by negative 4 to get 8, positive 8. And 1 less than negative 2 is negative 3, so that's my new power. And then I have plus 5/3, that's my coefficient, and then I'm going to do my power rule on x to the minus 1/2. So I bring down the minus 1/2. I have to do some multiplying here. I'll do that in a second. And then I have to subtract 1 from a negative 1/2. So for this, you're going to want to think minus 1/2 minus 2 over 2. And that's minus 3 over 2. So now I'm going to clean this up a little bit. I'm going to multiply this out. So, and I'm going to stick this back in the denominator because it's negative. So this is 4 over 3x to the 2/3. I'm going to put this back in the denominator, so that's going to be 8 over x cubed. I'm going to multiply this out, so I'm going to have a minus sign, and I'm going to have 5 over 6. And I'm going to put this back in the bottom, 5 over 6x to the 3/2. And I know we had a radical up in the original expression. Don't worry about putting the radical back. Just leave them as fractional powers. So at this point, you're going to want to pause the video because I'm going to start the solution to number 5. So you're going to want to try 5 first, and then so pause the video to try 5 first, and then come back to see the solution to 5. So here's the solution for question 5. We could FOIL this out and combine like terms and then just do the power rule, but FOIL is it might be too much work. We're going to try the product rule here. So remember the product rule, we've got a u times a v. So this is function u because it's listed first, and this is function v because it's listed second. And so we need to do the derivative of u times v plus u times the derivative of v. So here's the derivative of u, 3x squared times v, and then plus here's u times the derivative of v, which is 8x cubed minus 4. And then really you can just stop here. That is the derivative, and you don't need to do anything. However, these type of questions appear a lot in multiple choices, and so when the multiple choice answer is going to be simplified. So let's just simplify it to see what it is. So I'm going to distribute 3x squared in that first expression, and then I'm going to go ahead and FOIL this out, and I'm going to combine my terms. So I combined my powers of 6, I combined my powers of 3, and I had a power of 2 that I didn't have anything to combine with, and then I had my 12. So at this point, this is the answer to number 5, and if this were a multiple choice question, this is what you would see as the answer choice. So at this point, you might want to pause the video and try 6. 6 is connected to 5, so I'm going to start the solution to 6 shortly. So for question 6, it says find the derivative of function y for question 5. So here's function y for question 5. Find its derivative and evaluate it at 0. So here's the derivative, and to evaluate this at 0 means to plug 0 in for x. So we're going to plug 0 in for x, in all those locations and evaluate this. And when we do, all of these terms are 0, except for the last term is 12. So the derivative, or the slope of the tangent line to this curve, whatever this curve looks like, is 12 as we pass through x equals 0. So at this point, you should try question 7. And you're going to need a quotient rule. And the key to the quotient rule problems is when you simplify, you only simplify the top. You leave the bottom, you just leave the bottom v squared. So why don't you go ahead and pause the video and try 7, and I will start the solution shortly. Okay, so the solution to 7 is using the quotient rule. And like I mentioned at the beginning of the example, when we say simplify, we only simplify the top of the derivative, not the bottom. And again, like I mentioned in an earlier example, number 7 is a lot of these derivative questions are multiple choice questions. So the simplifying in the right way is really important. So notice that this is different than a number 2. This can't be, well, it can be rewritten to eliminate the fraction, but then you'd have to do the product rule anyway. So, you know, it's probably just as easily at this point to do the quotient rule. Okay, so let's do the quotient rule then. Remember, we got to think low d high minus high d low over low squared. And low is the bottom, which we call function v, and high is the top, which we call function u. So low d high is t plus 1 times the derivative of the high, which is 2t plus 7. And then minus high d low is going to be the top function times the derivative of the low. So we've got t squared plus 7t minus 3. Derivative of the low is 1. So, and then it's over low squared, so it's over t plus 1 quantity squared. Notice I just leave this as t plus 1 quantity squared throughout this entire solution. I don't simplify this, I don't FOIL it out. And multiple choice questions, this will never be simplified unless we can factor out a t plus 1 up here. Okay, so we're going to simplify the top though. That's the one thing we have to do. So we're going to need to FOIL this out. And distributing the 1 would be, and distributing the minus would just be basically changing all these signs. So we're going to FOIL that out. That's 2t squared plus 9t plus 7. And I multiplied through by 1. And then I'm going to multiply through by the negative. So we'll have 2t squared minus t squared is 1t squared. 9t minus 7t is 2t. And 7 plus 3 is 10. And then it's divided by t plus 1 squared. Notice the denominator never was simplified. Now, a quick caveat here. If this was factorable into t plus 1, t plus something, then we could cancel out a t plus 1 top and bottom. And that's a distinct possibility on the AP test as well. But this is not factorable, so we just leave it like this. So at this point, we're done with example 7. And you might want to pause the video now and try example 8, and I will start the solution shortly. Okay, so example 8 says find the horizontal tangents of this polynomial. So finding the horizontal tangents means finding the locations. If I say tangents, you should be thinking derivative, and if you're thinking derivative, you're thinking slope. And so what we're saying is we're finding the slope of the tangent line, and the slope is going to be horizontal, and that has a value of 0. So we find the derivative. So I gave you a nice polynomial here. You just have to do the power rule. So 6x squared minus 18x plus 12 plus 0, but I didn't write that. And now I'm going to set that equal to 0. Okay, so horizontal means what kind of slope? I say slope, you think derivative. So we have a slope of 0. So we're going to set the derivative equal to 0. That means we're finding where the tangent lines are horizontal. And this is factorable. So that when you look at things like this, every time you see a trinomial, you have to think, maybe I can factor this. So the first thing we want to do is factor out a 6. That makes the coefficients easier to see. And then we can see that this can factor into x minus 2 and x minus 1. So when we factor this and when we solve this factored form for our locations of our zeros, that means we have a 0 at 2 and a 0 at 1. So we have two locations where the tangent line is horizontal. And so if you can picture this polynomial as something that goes, up, down, and up, or down, up, and down, we'll have like a hill and a valley. That's where our tangent lines are horizontal. So at this point, we're done with example 8. And so for example 9, you might want to stop the video now and try example 9. And I'll begin the solution in just a second. So for example 9, I'm not quite sure why example 9 is not popping up here. Oh, I'm not quite done with example 8. Maybe that's why. It says find the horizontal tangents. They're at x equal 2 and x equal 1. Here's your function, your 2x cubed minus 9x squared plus 12x. So the horizontal tangents are here at x equals 1 and here at x equals 2. So this is just, I'm finishing up the question and giving you kind of a visual here. And they're equations, because when it says find the horizontal tangents, it's really wanting the equations. They're here and here, but their equations are equations of horizontal lines. So their equations are y equals 5. That's this one down here. And if we plug in 1 for everything, we get y equals 6. So those are the equations of the tangents. Sorry about that. I should have read the question a little more carefully. So these are the equations for the tangent lines. Okay, so I am going to start the solution to question 9 now. So if you haven't done question 9, you might want to pause the video at this time and try it. So question 9 is asking for a bunch of higher order derivatives. This is the rinse and repeat I was talking about at the beginning of the video. So I want the first, the second, the third, and the fourth derivative for this. So this is the function. Let's differentiate it. So if I differentiate this, I'm going to put my 8 out here, differentiate t cubed to get 3t squared, minus 4, and then differentiate this to get 5t to the fourth. And I'm going to simplify this. It's 24t squared minus 20t to the fourth. And I'm going to do this again. So the second derivative is differentiating this. So bring down the 2, that's 48t. Bring down the 4, that's minus 80t cubed. And I'm going to do this again. There's a second derivative, so there's the third derivative, 48 and negative 240t squared. And then the last derivative I'm asking for is a differentiated again. Derivative of 48 is 0. This term, bring down the 2, you get negative 480t. So we just found the first 4 derivatives of this polynomial. And we could differentiate it again and get negative 480, and differentiate it again and get 0. At that point, we can't differentiate it any longer. So at this point, hopefully that helps you with your fluency and using your differentiation rules. Just remember a couple of key strategies, and that is roots can be written as fractional powers. Variables that appear in the denominator a lot of times their powers can be negative and they can be put in the numerator, so you can do the power rule. And then, of course, the product and the quotient rule.